All right, guys, let's get started. Sorry, good morning or good afternoon, chemists. Let's get started. So a couple of announcements. So there's still a little bit more time. I extended the due date for this engineer course survey. So please do, it's on your assignments. I extended it until later today. It's free, 10 points for your online homework. So do expect one of these about every other week. I've reached out to your advisors to get more information and more questionnaire questions to ask you guys, because I do want feedback to make this class more enjoyable and make it and design it in such a way that you get more out of it. All right. So there's that. Also, on your to-do list, you might see a new page, a new thing on your to-do list, and that is to look at a page I posted under our course module. So you know this is where we get our lecture material, lecture slides. But here's this new, oh, why didn't you tell me? Why didn't you say anything? You didn't say anything. Because I can't see it on my thing. You gotta tell me. All right, so there's a new module under our course module, and that is midterm exam resources, because 2 weeks from yesterday evening is our first midterm exam, which will cover chapters 1 through 4, and we're on track to do that. So I want you to look at this page. I put it on your to-do list. You have to click on that page in order for that topic in your to-do list to go away, because all the information you need about the exam is on this page. It's kind of long, but I want all your questions to be answered here. You know, like where our exam is. Here's the exact copy of the supplemental information you will receive at the exam. It's the exact one. So you'll know exactly what information you will get on the midterm. So no questions of, will I get this equation? Will I get this conversion? It's literally right here, right? So everything is right here. So during your studies, you should be referring to this knowing, oh, I'll be given this piece of information. Oh, I'll be given this unit. All right, so it's all right there. There is a link to a Respondus test quiz where you actually have to download Respondus lockdown browser on your iPad or your laptop or whatever, and you'll do that quiz here. There's instructions on how to download it, how to set it up. The password to this test quiz is test. But when you take this quiz, it'll walk you through the different types of test questions that I write within our Carmen quiz exam. So multiple choice, numerical input, pull down menu, things like that. So it has some sample questions on what to expect. All right, so you'll see what Respondus lockdown browser looks like, right? So you have to do that test quiz. So you got 2 weeks to do that. And then finally, the most anticipated thing is I have 3 practice exams already posted with keys. The first one is a Carmen practice exam. So it's a quiz, all right? So it's in the exact style as what to expect on the midterm exam. The only thing is that I don't have this under lockdown browser because I think it's like annoying. So it's just a regular Carmen quiz. I don't have a time limit on it because some of you get different time limits for SLDS, so do time yourself. But it's here, all right? So the, multiple choice, drop down menu, numerical. So there's one Carmen quiz. Also, it's 1 question per page, FYI. You can take it as many times as you want. And then I have 2 paper practice midterms because these are easier and faster for me to write. So I like the paper ones, although the question types you won't see. They're all multiple choice essentially on these paper ones. All right. So is that enough practice exams for you all? Okay. If not, all right, if you don't have enough practice exams, also my overview sheets and the keys are additional sources of practice exams. So tons of resources for you. Oh, I guess the number 1 question is how many questions is this midterm? It's 30 questions. Each of these practice midterms are also 30 questions. So that's fair game for a 70-minute exam. All right. Okay. Any questions? Oh, yeah. No. So the quick answer is no, but I'll comment on that. So the question was, for numerical input, is there any partial credit? No, there's not. Yeah, my keys are intense. Okay, it's like a circus in there, but I try to put all the information you need to learn from the key. So for example, a numerical input question, I'm trying to look for one. Not those ones. Here, this one. All right, so it's a stoichiometry question. All right, and so there's the answer. You need to put in 53.2, but what you see here is a tolerance that I can set on the question, so it will accept answers between this little range. It essentially accounts for rounding errors. All right, but there's some instances where I don't have a tolerance. So I have like a sig fig question in here. All right, like you gotta get the, or here, balance this reaction, report the sum of the coefficients. I'm not going to accept any number other than 16. All right, so there's no tolerance there. And so it is right or wrong. There's 30 questions. They are all equally weighted. They're all equally weighted. So let's say you can't for the life of you do empirical formula calculations. At that point, maybe it's better to just take the L. It's only going to be one question. All right, skip it, come back to it later. It's only worth 1 point. So in that case, like if you get to empirical formula, if it takes you 20 minutes to do that one question, it's not worth it to you, all right, point wise. So do keep that in mind. Do keep that in mind. Everything is worth 1 point each question. There is partial credit for multi-part questions, and I can't really find here, this one. So in this question, question 11, see how there's 3 blanks. So this question, you could possibly get partial credit if you got the number of carbons right, the hydrogen and oxygen wrong. You can get partial credit for those partial or like multi-choice questions. Okay. All right. So let's go back to what? Chapter 3. Okay, where we're on chemical reactions. We're going to learn here more about the mole in a minute. So the idea here is we have 5 different types of reactions that I have what to look for. So in this section, we're balancing chemical reactions. We talked about balancing chemical reactions here. We looked at this particle diagram. We want to signify or communicate the lowest ratio of components reacting with one another. So we saw here we had 4 particles reacting to give us 4 particles on the other side. So we just simplified it to say a 1-to-1 ratio. We balanced a chemical equation for the complete combustion of propane. So there's one of our reaction types, combustion reactions, because everybody loves combustion reactions. Let's balance another combustion reaction and then do a combustion reaction. What do you want to do first? Do or balance? Do or balance? Do. Okay, we'll do it first so y'all can wake up. All right, so let's focus on this one right here. Liquid methanol, and I gave you the formula because I'm nice, undergoes complete combustion to form gaseous products. So they did not give me a coat. So tell my cats I love them. No. Okay, so although I don't, it's not methanol, it's ethanol, but whatever. Okay, whatever. So we're going to do a combustion reaction. So combustion means what? A hydrocarbon reacting with what? Oxygen. Yeah, so that is implied. So although it's not written, I can just say combustion reaction. You should know that it's a reaction with oxygen gas in the atmosphere. What are our products? What are our products? I didn't tell you, but what are the products in our combustion reaction? Oh, thank you. Thank you. Yeah, I was where I told them to tell my cats I loved them. Great. Okay, great. So if I catch on fire, you use that. Yes. Tap, pull, aim, squeeze. Okay. So I just shook up this container. It has ethanol in it, like kind of seeped out. So I'm just vaporizing the ethanol. All right, I got my goggles on. So there we go. I'm just going to pour out the extra liquid because we don't want to combust that. What are our products? Did you tell me what the products are yet? No, you didn't. What are the no, just tell me what are the identity of the products. Water and carbon dioxide. So, oh, they were supposed to give me a stick. Usually it's a stick. I'm kind of scared. Okay, all right. Okay, so that was a combustion reaction. Is that what you thought was going to happen? Kind of? Okay, yeah. So what we saw is the flame kind of went from the top to the bottom. This reaction has 2 reactants. the fuel, the ethanol, and oxygen. Oxygen can only come in from where? The top. So that's why it started from the top, went all the way to the bottom. So there we go. There's our combustion reaction. We did that first. So let's balance it now. So we already identified. So we're balancing methanol here, but no problem. So there's our reactant. What am I missing here? What am I missing? Water and CO2, but I'm also missing something else. What is also a component of balanced chemical reactions? The coefficients and the states. Yeah, and I even told you the states here. So liquid methanol. So we want to say liquid. Oxygen. I hope you know that oxygen, diatomic oxygen, is a gas, right? And I said gaseous products. So both CO2 and water are gases. So the strategy here for all combustion reactions, so you will always be right, is you balance carbons first, you balance hydrogens next, then you balance oxygens last by just changing the coefficient in front of O2. If there's a fraction, multiply everything by 2. If there's not, then that's it. So let's do that. So we balance carbons first. So what's the coefficient in front of CO2? Just 1. Okay, what about the coefficient in front of water? So be careful. On the reactant side, there's only one source of hydrogen. That's our methanol, but it's written a little bit funny. So how many total hydrogen atoms are here in this molecule? 4. So we want to put a 2 in front of water because each water has 2 hydrogens. Okay, so we're done with the product side. We're done. So the best thing to do is just to count up, take inventory of those oxygens. CO2 is giving me 2 oxygens while water is giving us another 2 oxygens. So there's 4 oxygens on the product side. I need 4 oxygens on my reactant side. So I need to think about how will I achieve that? So, you know, you might just want to put a 2 in front of O2 to get 4 oxygens, but is that right? No, we have to be really careful here. There's an oxygen coming from the molecule itself, but there's no worry here. All you need to think about is, okay, whoops, I need 4 oxygens total. 1 oxygen is coming from methanol. How many oxygens need to come from that O2 to equal 4? 3, yeah. So then we want a 3 halves oxygen gas there. All right. We're almost balanced. We just want to go one step further here and multiply everything by 2 because we don't like that fraction. When there's no coefficient, what number is implied there? Just a 1. So do know when you multiply everything by 2, the new coefficient in front of methanol is 2, the new one in front of oxygen is 3, 2, and then 4. All right. And so on an exam, how we would, how I would ask it, I would say, what is the sum of the coefficients? Because there's lots of places for you to go wrong here. All right, so the sum would be 11. 11, yeah. Okay. All right, so there's their combustion reaction. All right, so let's do a couple more of these. Each one of our reaction types 5 are represented here. So the next one, aluminum metal reacts with chlorine gas to form a single ionic compound. So to me, it sounds like we have aluminum as a reactant. What's the physical state of aluminum? It's a solid. Yeah, it says it's a metal, and metals typically are solids. All right, so let's not overthink this. With chlorine gas. So when I write chlorine gas, is it just Cl gas? It's Cl2. Yeah, so chlorine is one of our diatomics. Our diatomics on the periodic table are nitrogen, oxygen, fluorine, chlorine, and bromine, and iodine. It makes like a 7 on the periodic table. So those are our reactants. And now we want to predict the product, but I don't give it to you. You need to figure it out. All right, it just says an ionic compound. But, you know, we already got through chapter 2 where we predicted ionic compounds. I have a metal and a non-metal. Can I predict the charges that come from aluminum when it's in an ionic compound? Can I predict oxygen when it's in, or sorry, chlorine when it's in an ionic compound? Aluminum is typically what? As an ion. Aluminum, what charge? 3+, because it's in group 3. It's a metal, it's in group 3. It's kind of something that not necessarily needs to be memorized, but it's trends that metals, they take on their group number charge. What about chlorine as an ion? What charge does it usually adopt? Chlorides. +1, -1. Yeah, chlorine is a non-metal. So nonmetals typically form anions, a negative charge, because chlorine is group 7. All group 7s make -1. So those are the charges we have to work with. So our product is going to be the ionic compound formed from those things. So we have aluminum, and then how many chlorines? 3 of them, in order for it to be charge balanced. Ionic compounds are typically solids as well, because salts like NaCl are solids there. Right, so we've identified things. That was the hard part. Now it's balancing it. I just kind of look at the chlorines here because they're all messed up. There's 2 here, 3 there. So I'm going to put a 3 in front of diatomic chlorine, a 2 in front of the regular aluminum chloride. And then since I messed up alumina, I'll put a 2 there. So I like to save the simple things for last, like especially if it's one element, save that for last. All right, how was that? Okay, so this is reviewing naming, turning sentences into formulas. Definitely a tough task. All right, so this next one, mercury oxide is heated and decomposes to elemental mercury and oxygen gas. Okay, I know some of those things. Elemental mercury is Hg, and oxygen gas is O2. Oh, gas. Oh, and I tell you mercury is a liquid. Wow, there we go. Those are my products. They're just elements off the periodic table. What the hard part here is I give you a name of a compound. What kind of compound is that? Mercury 2 oxide. What kind of compound? What kind of naming scheme does it use? If there's a stock system there, that means that mercury needs to be a cation. It has to be Hg2+. So this is what kind of compound? Molecular or ionic? Has to be ionic because an ion is present there. All right. So from the name, we know that mercury 2+ is involved. What about oxide? Oxide or oxygen typically adopts what charge? 2-. So although just I give you the name, we can infer what that compound is. So hopefully you can see those 2 charges are in fact charge balanced. So just be HgO, and this would be a solid. In this case, although the question doesn't really imply that, right? So we're almost done. We've identified everything. Again, the hard part now, it's just for balancing. I have some oxygen, so I'm going to put a 2 in front of the mercury oxide. And now I've messed up mercury, so I'll put a 2 in front of the elemental mercury on the product side. What's harder, identifying or balancing? What do we think? What? Okay, I hear 50-50. All right, so definitely just practice. I think it's the identifying what's involved, right? Because is it a molecular naming scheme? Is it an ionic naming scheme? We sometimes have to predict charges. Definitely chapter 2 review. Okay, so let's do some other ones here. I'm actually going to skip this one because we're going to do it again later. Let's just do this last one here. Metal magnesium will react with an aqueous solution of aluminum chloride to produce aluminum solid and an aqueous solution of magnesium chloride. So tons of names. So again, chapter 2 review. So let's just go through what are our reactants and products. So we have a ribbon of magnesium. So that to me, that just sounds like elemental magnesium. So magnesium solid. So if we keep going, it reacts with aqueous aluminum chloride. So is aqueous aluminum chloride, is that a reactant or product? How it's worded. We got to think about our communication skills. It's a reactant because it reacts with magnesium. Yes. So how do we write that? I know it's aqueous, so I know the state, but the problem is I give you the name. Aluminum chloride, we already actually talked about this. Aluminum is a metal. It typically adopts the +3 charge. Chloride is -1. So we, from the name, can deduce that this is AlCl3 again. All right, just from the name itself. All right. the tri part is not implied at all. The 3 chlorides is not implied at all in the name. And that's specific of ionic compounds. We need to know those charges. All right, and we produce, so meaning arrow, aluminum solid, so again, the element, and an aqueous solution of sodium chloride. So I have AQ again for that other product. Magnesium chloride is ionic again. But we need to predict the charges. It might be easy to think, oh, I'm just going to slap those 2 elements together, magnesium and chlorine, but this is not actually charge balanced. We need to think a little bit deeper. Magnesium is typically what charge? +2, because why? Because you memorized it? No, because magnesium is in group 2A. So it's a 2+ cation, and chloride is -1. So it's not just MgCl, as written, no, it's MgCl2 in order for it to be charge balanced. Okay, there we go. All right, the hard part's done. Naming, identifying. Now it's the balancing. Okay, again, I'm gonna balance the chlorines first because they're like wrapped in something, and I'm gonna leave the elements for last. So it's like a 2 to 3 thing again. So if I put 2 aluminum chlorides and 3 magnesium chlorides, I have 6 chlorines on each side. Now I can just balance with those free elements. I need 3 magnesiums and 2 aluminums. There it is. Okay. I think the naming part's hard. Lots of ionic things to throw around, all right? Would you have just slapped Mg and Cl together, all right, and called it a day? Or would you have known that, hey, that's an ionic compound, so that ionic compound needs to be charge balanced. So that means I need to predict the charges of those metals and nonmetals. There's a lot going on there. All right, so equations is due on Monday, balancing stuff and whatnot. Okay, so with that last question, the reaction involved in aqueous solution. So we did, the combustion reaction with methanol, ethanol, that was a combustion reaction. The states of matter were like liquids and gases. What makes this last question a little bit different that we did is we had solids in an aqueous solution. Aqueous solution just means dissolved in. Reactions that happen in water. When we think about NaCl, okay, NaCl is like our prototypical solution, right? Solid salt. So in your mind, do you know what that looks like? Solid salt. Yeah. Put it in water. If you put that in water and dissolve it, what do you make? Salt water. Yeah. So that's a mixture. And so that's what this part of the chapter, solution chemistry, investigating, okay, what is the nature of these mixtures, these solutions? When we put and dissolve salt in water, we make what's called an aqueous solution, where the salt is no longer a solid. It's actually dissolved in the water itself, in that liquid water. In your mind, think about what a glass of water looks like and a glass of salt water looks like. Does it look any different? No, they don't, but you'll see vastly different properties here when we have pure water versus sodium chloride that's actually dissolved. So that sodium chloride is what we call the solute. It's the material that's dissolved in the solvent. So remember, solution just means any homogeneous mixture. We need 2 things present, right? Typically, at least 2. So like a solute, something like salt, sugar, you can dissolve that in water, which is our solvent, and it determines the phase. So the interesting thing here about solutions is, so these little diagrams show how substances can dissolve in water. We can't actually see these particles, all right? Because again, when you think of salt water, sugar water, regular water, they all look the same, but they have vastly different properties. And so when we have these things dissolved in water, we call them aqueous solutions. We give it that AQ designation. All right. So when I write NaCl AQ, what is implied is that we have salt, solid, and water present. This is a fancy way of saying salt water versus solid salt, like in your salt shaker, much different appearance. All right. So what do things look like when you dissolve them in water? We need to think about, again, we can't see particles. Okay, we can't see atoms, but we can see some of their behaviors. Oh, this is kind of scary. Okay, so we have different types of what we call electrolytes, meaning ions dissolved in solution. When you have free ions, so like cations, anions in solution, when they're free like that, electrons can move, okay, across the solution, across the water, and conduct electricity, right? Okay, so when we think about electrolyte solutions, we have free ions, it conducts electricity. So we can measure electrolyte behavior in terms of conductivity. So some definitions here. Any electrolyte is just any solution that contains ions. And what I mean by ions, cations and anions, all right? Any amount. These solutions will conduct electricity. But underneath that, we have different types. We have strong electrolytes. These solutions, when you dissolve that substance, that solid or whatever, into solution, only ions are present in solution. Weak electrolytes, on the other hand, they still conduct electricity when you dissolve them in water. They just don't form as many free ions in solution, right? So strong electrolytes, all ions, weak electrolytes, some ions, some intact molecules. And then finally, non-electrolytes, they don't conduct electricity at all because there are no ions present. So you can look at these pictures here. This picture would depict what kind of electrolyte right there? Strong, weak, or non? Strong, yeah, because everything in the beaker is an ion. Versus the one at the bottom here is what kind of electrolyte? Non. So is it gonna conduct electricity? No, because there are no ions present in solution. But what about the middle one? This would be a weak electrolyte because look, you can see some ions, some neutral molecules. So if we compare a strong and a weak electrolyte, which one's gonna conduct electricity more, strong or weak? Strong, yeah, more ions, more conductivity. So let's look at examples here. So I have strong, weak, and non. In the margin here, I would write these down. These are the things, compositions you want to look for when trying to identify whether something is a strong, non, or weak electrolyte. Okay, all strong electrolytes are ionic compounds or strong acids. We'll talk about that later. Okay, all ionic compounds are strong electrolytes, all. Okay, and all strong acids and bases. Okay, non-electrolytes on the other hand, so all of these things will always break up into ions. You can see the example here. NaCl, is that ionic? Yes, it is. So is it a strong electrolyte? Yes, it is. So what that looks like in solution is you take your NaCl solid, it becomes aqueous, but what this actually means is you have free sodium plus and chloride minus. HCl is an example of a strong acid. So the same idea here is in act as well. HCl, that molecule they're not attached to one another. In solution, you'll actually see free H pluses floating around and free chloride minuses floating around. So basically you only see the product side of this reaction if you were to look into your solution at the particle level. NaCl, same thing. You don't see Na and Cl bonded together in solution. They're actually floating around freely. Versus a non-electrolyte like sucrose. This is sucrose. Sucrose is a molecular compound. We use molecular naming rules. Are there any ions present in molecular compounds? There are not. Only ionic compounds have ions. So when you dissolve sugar, does sugar dissolve in water? It does. But the difference here is that sugar does not produce any ions. So when I turn the sugar into dissolved sugar water, there are no ions. So will electricity be, will this solution be conductive if there are no ions? No, there are not. Yes. So those are strong versus non-electrolytes. So let me just show you the example. Actually, let's talk about a misconception here. I feel like the idea is like water and electricity don't mix, right? But let's look at our criteria. Let's think about pure, wow, this chalk sucks. Okay. If I had pure water, what kind of naming rules would you use to name water? Would you use ionic? Would you use molecular? What's its composition? Ionic compounds are typically metals and nonmetals. Are there any metals here? No. So what kind of compound is this? It's molecular. So based upon our criteria, is it a strong electrolyte or a non-electrolyte? It's technically a non-electrolyte. Yeah, that's for pure water. So let's look. Okay, so I got my conductivity tester. So the brightness of the light will tell you the extent of free ions present. So I have pure water. Okay, so what do we think is gonna happen? Nothing. But what about the idea that water and electricity don't mix? What's wrong with that idea? The water that you and I, us mere mortals, interact with in everyday life is not pure water. It's not. There's things dissolved in it, minerals, ions, things like that. So this is distilled water. We paid money for this to take all the ions out. This is tap water. It came from the sink, okay? Sink water, when you think about like hardness, chloride content, things like that, this is just regular sink water. So let's see what happens. Oh, there it goes. Whoa, yeah. So the idea that water and electricity don't mix, it's true when thinking about tap water, but water on a molecular level, because it is a molecular compound on its own, is a non-electrolyte. Okay, so there's water. All right, so let's look at sugar and salt. So I just went to, this is from Wendy's. This is a salt container, or like a little bit of salt. Okay, so I'm gonna just dissolve some salt into this pure distilled water. And then here is a sugar packet. All right, sugar packet. Putting into distilled water. So based upon the identities, salt, NaCl, sugar, C12H, whatever, you know, what do we think is gonna happen? I'll do them at the same time. Is one gonna light up? Or both of them gonna light up? Or none? Yeah, what do we think? What do we think? Okay, all right, so this one's salt. This one's salt in this hand. Okay, let's see what happens. Boom. Okay, dang, that's bright. So that's salt, and I'll just to prove it to you, this one's sugar. All right, so sugar doesn't do nothing because there's no free ions for conductivity to occur. Okay, there we go. So those two, I need to clean these. I'm gonna come back to this demo in a little bit. So their composition absolutely tells us something about their properties on the molecular level. Okay, so I did strong, I did non. The one I didn't do yet was weak. So what makes a weak electrolyte a weak electrolyte? So we look for weak acids and bases, which we'll talk about a little bit further here. So the idea here is strong electrolytes, we have all ions in solution. Weak electrolytes, we only have some ions in solution. HF, hydrofluoric acid, is an example of a weak electrolyte. So when you put HF into solution, only some of those HF molecules break apart. So basically with this equation, see how the arrow is different? See how I chose a different arrow? That is deliberate. I'm trying to tell you that both sides of this reaction happens at the same time. So, or they both exist at the same time, meaning that there are ions present and neutral molecules. So when you look at the particle diagram here, see how both sides exist at the same time? We have ions and the neutral molecule. So weak electrolytes typically do not conduct as much electricity. You won't see as bright a light for these examples. So I'll show it when I talk about strong and weak acids. Okay, so those are electrolytes. Okay, so think about, brightness of light relating to conductivity and amount of ions present. Okay, so ionic compounds and these two types of reactions, double displacement reactions and whatnot, these reactions are dictated by typically solubility, forming some type of product. On the product side, that's a solid, liquid, or gas in order for a double displacement reaction to occur. We have ions present, and typically they're swapping partners. And so when a solid, liquid, or gas is formed in the product side, typically a driving double displacement reaction will occur. So I want to show you this solubility table and how to use it. You will always be given this table on the exam. You see it on the supplemental information. The only thing that's missing here, see how there's the names? I don't have the names. I basically X'd out the names. You only have the formulas. So the formulas are there, not the names. So basically, when we have a double displacement reaction, you know, we have two sets of cations and anions reacting with one another, and they swap partners. Our ions will only swap when one of the products is a solid, liquid, or gas. So this table tells us what substances, what ionic substances form solids or are typically soluble in water. So how we read this table is we look at the different anions listed here. These top ones are usually soluble in water. Here are the exceptions. So things that are soluble in water will always get the aqueous designation in our balanced chemical formula. When things are insoluble in water, they don't dissolve in water. So they get the solid designation. All right. Do note the exceptions. There's some exceptions that you'll have to see. All right. So let's predict whether these things are soluble or insoluble in water. So locate calcium nitrate on the table. So if we look here, nitrate is right here. So is calcium nitrate soluble or insoluble in water? Soluble, yeah, because it's not one of the exceptions. So if it's soluble, what designation does it get in our formula? Aqueous. It'll get AQ, meaning it's soluble. What about KBr? Aqueous or solid? It is also aqueous. So if you look at where bromide is here, potassium's not an exception. What about AgBr, silver bromide? Aqueous or solid, according to the table? Solid, yeah. So you might look and see, oh wait, but a bromide is usually soluble. But if you look over to the right, it's one of silver bromide is one of the exceptions there. Okay, so yeah, silver bromide is a solid. What about barium sulfate? Sulfate, barium is an exception, so there is a solid again. Magnesium hydroxide. So hydroxide is here. So it's under the usually insoluble, and magnesium is not an exception. So there's another solid. And then ammonium hydroxide. What you see here is that basically all ammonium and group 1 cations, they're always soluble. So this one is aqueous as well. All right, so just practice using the table given certain ionic compounds. Identify the cation and anion, do check for those exceptions. Okay, so now how do we balance a precipitation reaction or double displacement reaction? It's all about identifying the ions, their charges, and forming neutral products, all right? So the idea here is, the first step here is identify your cations and anions that you're swapping. You want to then swap them and form your new products. Adjust the subscripts in your products to make sure your product is charge balanced. Okay, we adjust subscripts to make sure charges balance out. Where the balancing of the coefficients come into play is when we actually want to balance all of the atoms. So when we balance the overall equation, then that's when we start adjusting coefficients. So my tip is here, because we're sometimes balancing polyatomics. If you have a nitrate on a reactant side and a nitrate on the product side, just treat that nitrate as like one thing, right? You don't have to balance the individual nitrogens and oxygens, just treat it as one thing. I have like 2 nitrates on one side, 2 nitrates on the other side. So just kind of balance it as a unit. It's a lot easier that way. So once you have identified everything, everything's charge balanced, your atoms are balanced as well. Now we need to determine phases. You might already know that the reactants are aqueous, but you need to predict the phases of the solids that you produce. So again, using that table, something needs to be a solid. If nothing on your product side is a solid, then no reaction actually happens. And I'll show you why. It's basically because there's no driving force. All right, so let's do some examples. Okay, so this is the one we skipped earlier. I wanted to do it here because it's harder, because I just tell you the reactants. So let's write the balanced chemical reaction between aqueous lead nitrate and aqueous potassium iodide. So again, names to formulas. Crap. So lead 2 nitrate. What's the charge of lead? 2+. I love the stock system. Nitrate is NO3-. So we need to write that reactant so it's charge balanced. We use subscripts. So it's lead, nitrate, 2 of them. What's the state? The question says it's aqueous, but you can check on the table too. You'll see that all nitrates are aqueous. Okay, so that's one reactant. Now we need the other one. Aqueous potassium iodide. Potassium takes on what charge as a cation? +1, iodide -1. So it's just Ki to be charge balanced. We also put the state here. So aqueous again. Great. So now we have the reactants. Now we need to predict the products, but we already kind of did the hard part. The products is where the ions just swap partners. So K is now going to go with nitrate. Lead is now going to go with iodide. I already have the charges written here. The charges do not change. So I'm combining lead and iodide. So what's the formula there for it to be charge balanced? It has to be lead, how many of them? 2 of them. Yeah, so the charges are not changing. We need to adjust subscripts in order for things to be charge balanced. And then our other product is what? What's the other partner? Nitrate and K. So what's the ratio there? Just 1:1. So KNO3. That's it, right? We've identified everything. Everything is charge balanced. Now we can adjust coefficients to make sure the atoms and the groups actually match on each side. So going through this, I see there's 2 iodides on lead iodide. So I'm going to put 2 in front of Ki. So then there's 2 iodides on the reactant side. I screwed up K, so I need to put a K or a 2 in front of lead or potassium nitrate. And that's great because now I have 2 nitrate groups, and I have 2 nitrate groups on my reactant side. So now it's all balanced. So it's great. So the big idea here is that subscripts related to identity, coefficients related to just balancing the groups and the atoms. All right. Oh, I'm not done. What did I forget? The states. Yeah, the states. So I have the 2 products. I need to know which one, which is the solid and which one is aqueous. Do I have to just memorize that? No, I use the table. So from the table, do you know which one is the solid? We know which one's the solid. So let's look at iodide here. Okay. Iodides are typically soluble, but lead is an exception. So lead iodide is the solid here. And then if you look at nitrates are always aqueous. All right, they're always soluble. So we do have 1 solid being formed here. Great. And so this is what it looks like. It's this yellow solid lead. Usually lead containing compounds are bright yellow, like our school bus yellow color. All right, so that's our double displacement reaction. There's the strategy to do it. It's all about ions, okay? Balancing, charge balancing, knowing those charges. All right, so we wrote a double displacement reaction, but let's think about another way to represent reactions that happen in solution. So in this reaction, everything is charge neutral, all right? Lead nitrate, do you think this would conduct electricity? This solution, if you just had it in a beaker and I stuck it under my thing, would this conduct electricity? Yes. What's the criteria for strong electrolytes? They have to be blank. Ionic. Is this ionic? Yes. Would Ki conduct electricity? Ki is what kind of substance? Ionic. We named it using ionic naming rules. Will this conduct electricity? Yes, because there's free ions present. Same thing with potassium nitrate. All of these are ions. So how we've written this balanced chemical equation isn't quite right, because in water, Ki stuck together doesn't exist. It actually exists as K plus and I minus free ions floating around in solution for the strong electrolyte character to be seen. So the other way to represent reactions in solution is to use full or net ionic equations where we think about how these particles actually exist in solution. So a full ionic equation, the thing is you need to start with a balanced chemical equation. Then you want to identify and split any substances that are both strong electrolytes and aqueous. They have to be two things, strong electrolytes and aqueous. We split those ions. Then once we have the full ionic equation, then we identify spectator ions, ions that don't change on either side. We remove those and we get the net ionic equation. And that's what describes what really happens in solution. So I think it's easier to just do the problem. Okay, so let's revisit this question. I have the balanced equation for you, and there's the strategy. So we have our balanced equation. Now we want to write our full ionic equation. So the hardest part here is to determine what do we have to split. Okay, we only split things that are strong electrolytes and aqueous. They have to be both of those things. They can't just be one. So let's go through these. Do we split up lead nitrate? Do we split that? Well, okay. Is lead nitrate a strong electrolyte? Okay, what constitutes a strong electrolyte? It has to be ionic or a strong acid or base, right? So is lead nitrate a strong electrolyte? Yes. Is it aqueous? Yes. So do we split it? Yes, we do. So we split this. So what that looks like is we have a lead 2+ and 2 nitrates. And all of this is aqueous. I'm just being lazy and removing this. Okay, let's do the next one. Ki. Is Ki a strong electrolyte? Yes, it is. Is it aqueous? Yes, it is. So do we split it? Yes, we do. So we split Ki too. So, but how do we split it? Do we just get 1 K+ and 1 I-? No, we actually get 2 of them because there's literally 2 of those formula units there. So we have 2 K+ and 2 I-. Following? Okay, let's keep going. All right, lead iodide, lead 2 iodide. Is lead iodide a strong electrolyte? Yes, because it's ionic. But is it aqueous? No. So do we split it? No, we don't. No split. No split. No split. Just keep it together. So just literally rewrite it. PBI2 solid. Okay. The last one, lead nitrate. Is it a strong electrolyte? Yes. Do you split it? Yes, because it's aqueous. So we split that one. Okay. So it's not just K+ and nitrate. It's 2 K+ and 2 nitrates. Okay, there we go. So this is a small detail. You might notice like, oh, they're all ionic. They're all strong electrolytes, right? But the detail here is that lead iodide is a solid that does not exist in solution as free ions. It's a solid at the bottom of the beaker, so we do not split it. The common mistake here for net ionics is students will get gung-ho about splitting all the ionic things, and they'll just split everything. They'll split this one too. But there's a problem where we identify spectator ions. So a spectator ion is anything that doesn't change from the reactants to the product side. So let's track lead. Does lead 2+ change to the product side? Yes. I- also changes. Now it's tied up in the solid. But let's look at nitrate. Does nitrate change at all from the reactant side to the product side? No, it's written exactly the same. Same thing with K+. See how it's written exactly the same on each side. So those are spectator ions. I'm going to remove those because they're not changing at all in the reaction. So they're not really involved. So I'll remove those spectator ions to get my net ionic equation, which is lead 2+ plus 2 I- gives us lead I2 solid. So that's my net ionic equation. So if you were, I'll take this away from you. If you were gung-ho and ended up splitting up lead iodide solid, because you're like, oh, it's ionic, but the idea here is a solid, you'll get that everything's a spectator, and then you'll be in trouble, right? So don't get caught up on that the things you split have to be 2 things, a strong electrolyte and aqueous, both. All right, so let's do another one. So sodium chloride and potassium nitrate. So we have sodium, it's positive, chloride, it's negative. Potassium, it's positive. Nitrate, it's negative. So I'm just going to swap my partners here. So my new charge balance substances are KCl and NaNO3. Okay. So there are my products. Let's get the states. So according to the table, KCl is what state? Solid or aqueous? From that table. I'm just going to tell you it's aqueous. Because chloride is here. Sodium is not or potassium is not an exception. What about sodium nitrate? Solid or aqueous? Aqueous. Again, because nitrates are typically soluble in water. All right. So first question, does this reaction happen? No, it doesn't, because there is no driving force. We did not form a solid, a liquid, or a gas at all. So this reaction doesn't occur, but I want to prove it to you. Let's try to write the net ionic equation. Okay, let's go through these. Would I split NaCl to get the full ionic equation? Would I split NaCl? Yes, we split that because it's ionic, strong electrolyte, and it's aqueous. Do we split potassium nitrate? Yes, we split that. Do we split KCl? Yes, because it's ionic and it's aqueous. Do we split sodium nitrate? Yes, we split everything. So just prove it to yourself. If you split everything, okay, and you compare the reactants and the product side, everything's a spectator ion, meaning nothing is involved in the reaction. Nothing occurs when you mix these two things together. The driving force in this reaction was the formation of that solid. That's what forced the new pairing of the ions, cation, anions together. All right, so there's an example of that. Okay, so other types of double displacement reactions involves acids and bases. So I told you the three types of driving forces are forming a solid, so precipitation, a liquid, in this case, it is neutralization reactions where we make water. That's forming of our liquid, and then gases, which are a special case. So let's talk about acids and bases. Acids can donate an H+. Bases can donate an OH-. So at its core, a acid-base reaction, H+ plus OH- gives us, what's our product? If you think about those in terms of ions. HOH, does that look familiar? That is H2O. The state of H2O is what? Is that aqueous? No, H2O is a straight up liquid, right? So in acid-base neutralization reactions, the driving force is forming liquid. In this case, it's almost always water because we have an H+ and an OH-. All right, so within acids and bases, there's different kinds, strong and weak. This is the easiest way to understand it. For the acids, in this class, there are 6 or 7 strong acids in the world. Everything else that's an acid is a weak acid. So if you memorize the 6 or 7 strong acids, any other acid you encounter is a weak acid. So here's the, this is from your book. These are their strong acids. HCl, so hydrochloric acid, nitric acid, sulfuric acid, perchloric acid. So you can see that there's like an anion attached to all of these, where H+ is the cation. So like we know chloride is typically Cl-. See how there's just one acidic proton attached? All right, where we have like H+ there. Nitrate is usually NO3-. So there's only one acidic proton or hydrogen attached to it. Then sulfuric acid, perchloric, hydrobromic, and hydroiodic. Some folks will also say chloric acid, so HClO3 is also a strong acid. So there's your 7th one. Different books say different things. So that means any other acid in the world is a weak acid. So acetic acid is what kind of acid, strong or weak? Weak, yeah. So within its naming, it's kind of gives you a glimpse into what type of electrolyte it is. Strong acids will dissociate fully into cations and anions. So you can see that there. It still follows the same idea of electrolytes. Strong acids, when like HCl breaks up into solution, you get H+ and the ion totally. You only get the product side. Versus weak acids like HF, you have both sides present. So strong acids actually conduct more electricity than weak acids. So let's look at an example here. All right, so I have HCl, and hydrofluoric acid is super bad for you. It'll like dissolve your bones. So I don't have that. I have a different weak acid, acetic acid, but it is in fact weak. So I have HCl, all right, HCl and acetic acid. So we said what kind of acid is HCl? Strong. So what kind of electrolyte is HCl? Strong. Okay. Acetic acid is what kind of acid? Weak. So it is what type of electrolyte? Weak. So how will the light go in terms of ions? HCl, acetic acid. Think about it in your head, and then I will do it. HCl. Okay, so there's HCl. Very bright. Let's do acetic acid. There we go. So you can see clearly from like the light that there's less ions present in acetic acid. They're made to the same concentration. So that's a small little detail. See, super bright because all ions. Acetic acid, not so bright because there's some ions, but some of them are still intact. Okay, there we go. So those are acids, HCl and acetic acid. Okay, so there's strong and weak acids. There's also strong and weak bases. They're easier to identify. Strong bases are essentially anything with a hydroxide anion slapped onto it. So any of our metal hydroxides. So for example, right here, you can see strong bases, all right, is any metal with a hydroxide attached to it. Sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide. That hydroxide is telling you, hey, there's straight up OH ions present. That's a strong base, all right? Versus weak bases, again, the idea of the electrolyte behavior that only some of it breaks up. Weak bases still produce OH minus, but in a different sense. We still have this double arrow equilibrium arrow where both sides of the reaction is present at the same time. So our two examples of weak bases that basically the only ones we care about in this class are ammonium and ammonia and methyl ammonia here. So we have NH3. What happens in this reaction, because it's kind of hard to see, you think about water being HOH again, essentially that nitrogen is grabbing one of those hydrogens, forming a new bond, NH4 ammonium, and a hydroxide on the end here. So this is why we call ammonia a base, because when you put it in water, it reacts with water to make that base unit. It's not actually on the molecule itself. So that's a little subtlety there. And then the same thing with methyl ammonia here, or methylamine. It's the same process. It's just there's a methyl group on it. So that nitrogen is going to grab one of those hydrogens and produce that hydroxide. All right. So the idea here is both sides of the reaction happens at the same time. They both exist. We have some ions and some neutral molecules. So I have two things. We're going to do it again. I have 1 molarity sodium hydroxide, 1 molarity sodium hydroxide. Sodium hydroxide is what kind of base? Strong. So what kind of electrolyte is it? Strong. Okay. So should it have good, poor, no conductivity? Good. Yeah, strong. Yeah, conductivity. Okay. Then I also have ammonia here, NH3. Same concentration. Ammonia is what kind of acid? Or sorry, base. Weak. So therefore, what kind of electrolyte? Weak. So what kind of conductivity should it have? Weak. Okay. Okay. See, sometimes being repetitive, but then the concept sticks, right? Yeah. Okay. So base, or sorry, sodium hydroxide, ammonia. So think about in your mind I'm gonna swap my hands. So this one's gonna be sodium hydroxide. This one's gonna be ammonia. Okay. So we'll do sodium hydroxide first. There we go. And then here's ammonia. It took a while for those electrons to go, right? Ammonia, here's sodium hydroxide. So hopefully you can clearly see which one has more ions present. Good. All right. And again, it's all based upon the composition, all right? In this case, ionic compounds, all strong electrolytes. Our bases and acids. Where's my water? Nope, that's HCl. I don't know where my distilled water is. Just tap water. Okay, just clean them off. All right, there are acids and bases. So do memorize those strong acids, because then everything else will be weak. Okay. All right, so let's tie it all together. Look at these electrolytes. What is it? This first picture, let's move left to right. So I like to break it down. What kind of electrolyte are you looking at? And then what substance will adopt that? So what are we looking at for this left one? Non, weak, strong, what? Non, yes, non. Okay, so non-electrolytes are typically what type of substances? Molecular substances. So like pure water, distilled water is actually a non-electrolyte, doesn't conduct electricity, but once it interacts with our world, things dissolve in it, then it becomes conductive. So water is a molecular compound, hydrogens and oxygens. So of these compounds, which ones will adopt this picture? There's only one molecular compound written there, and it's CO. HCl is what kind of electrolyte? It's actually a strong acid. So therefore it's a strong electrolyte. So it will not look like this. Yeah, there's two atoms there, but when dissolved in water, you will actually see H plus and Cl minus all in the water. They're not all stuck together like that. All right. So the next one, this picture represents what kind of electrolyte? Weak. Yes. So I guess the best thing to do is just go through this list and see, okay, what kind of electrolytes are they? NAF is what kind of electrolyte? It's ionic, so it has to be strong because it's ionic. What about HF? That's an acid. Is it one of our 7, 6, 7 strong? No, it is not. HF is not. It's HCl, HBr, and HI are the only like monoatomic acids. HF is actually a weak acid. If you're looking at the periodic table. So this is a weak acid. So HF would adopt this picture because we have both ions and intact molecules. This is a weak electrolyte. All right. And then the last one here, what's being depicted? A strong, weak, yes, strong, because it's all ions, but there's a subtlety here. We want the cation-anion ratio to be correct. So, oh no, it's fine. Everything's a +1, -1, never mind. Never mind. Okay. So this is a strong. So which one of these will adopt this picture? HI is what kind of substance? It's a strong acid, so therefore it's what kind of electrolyte? Strong. What about KBr? It's ionic. So what kind of electrolyte is it? Strong. So in this case, it's both of them. We'll adopt this picture. Okay. So that's how we relate conceptually, you know, on a particle level, what we're seeing here. Because don't all these freaking look like water? Okay. But we see real different properties based upon what substance we're dissolving and what kind of electrolyte it is based upon its composition. All right. So let's go back to neutralization reactions. All right. So we did the particle diagram. We can write net ionic equations for neutralization reactions too. We follow the exact same rules. So here we are reacting HCl aqueous and sodium hydroxide aqueous, and we're making our product. So again, think of your acids and bases as ions. We have H plus and hydroxide minus. So we're swapping ions just the same. So we see chloride will now go with sodium. H plus will go with OH. What is that when we combine H plus and OH? H2O, just straight up water, H2O. Do we know the state of that? Do we need to use our solubility table? Water is what state? Liquid, yes, yes. Let's not try to overthink it. But then our other product here is the other set of cations and anions. And so you see that it's sodium and chloride, and that is charge balance because it's minus and plus. So all those rules still apply here. So NaCl, I don't have the state of it, okay? So how do we figure out the state of NaCl? Solubility table again, but hopefully you know by this point that NaCl, does it dissolve in water? Yeah, it does. So it's going to be aqueous, but the solubility table will tell you it as well. All right. So there's my just the balanced equation, but we want to write the net ionic equation, the net ionic. So we need to go through and determine what things do we have to split. So we only split things that are strong electrolytes and aqueous. So HCl, do we split that? Yes, HCl is a strong acid and it's aqueous, so we split that. Do we split sodium hydroxide? Yes, because it's a strong base, strong electrolyte, and it's aqueous. Do we split up H2O? No, we don't, because it's a liquid. No split. Do we split up NaCl? Yes, we do. We split that. Okay. So if you do that, what you'll see, the spectator ions are chloride, sodium, sodium and chloride. So the net ionic equation for this chemical reaction is H plus OH minus gives us H2O liquid. And isn't that what I said? Like acid-base reactions at the core, what they are is an H plus combining with a hydroxide to give us a water molecule. So that salt, that NaCl, is just a bystander in this reaction that they need to be there in order for this reaction to be charge balanced. All right, so let's do another one. So here is a different acid-base neutralization reaction, but it's between nitric acid and calcium hydroxide. So these are just different acids and bases. It's still strong. They're still both strong. But let's go through these to see if we can't get the full ionic equation. Nitric acid, do we split that in the full ionic equation? Nitric, yes, it's a strong acid and it's aqueous, so we split that. What about calcium hydroxide, aqueous? Do we split that? Yes, we split that too because it is a strong base, or you can think it's ionic. It uses ionic naming rules and it's aqueous, so we split that. Do we split water? No. Do we split calcium nitrate? Yes, we do. We split that. Okay, because it's ionic and it's aqueous. So you can see I already did the splitting for you. H plus nitrate, calcium hydroxide. I didn't split water, and I split calcium and nitrate. So looking through these, can you identify the spectator ions? Spectators, calcium. It's the exact same on both sides. What else is a spectator? Nitrate. So rewriting this equation, we just rewrite it without these spectators. So you have 2H plus 2 hydroxides plus 2 H2O liquid. So you see for this net ionic equation, it's actually the exact same as the previous one. It's just that there's 2 of them. Yeah. Yeah, no, that's what it is. It's canceling out. That if you think of it like an equation, yes. Well, this is a chemical reaction equation. Yes, this one cancels out with that one cancels out with that one. But H plus, it does change on the other side. It's now tied up in that water, so we can't actually cancel it. Okay. Yeah, that's a good way to look at it. Okay, so let's look at another one here. Neutralization between a weak acid and a strong base. So same ideas here. Let's go through these and see, do we split them or not? HF, do we split that guy? Yes? What do you have to be in order to split it? It has to be 2 things. No. No. In order to split it in your full ionic equation, it has to be 2 things. A strong electrolyte and aqueous. Is HF a strong electrolyte? No, HF is a weak electrolyte. So do we split it? No, we don't. We no split. No split. Because it's a weak electrolyte. We only split things that are strong and aqueous. Do we split sodium hydroxide? Yes, you split that. Do you split water? No split. Okay. Do you split NaF? Yes. Okay. So so we keep together HF. Okay. So HF stays together. So that's the weird thing. We have Na plus, OH minus, giving us water. And then we do split up Na plus and F minus. Okay. So what are our spectators here? What can cancel out on both sides? Just the sodium. So if you look here, HF is together on the reactant side, but an ion on the reactant or on the product side. So we can't actually cancel that. That is not a spectator. We need to keep the those components. So when we rewrite this, it'll be HF aqueous plus hydroxide gives us water and fluoride minus. All right, so this is a small detail, and it's still an acid-base neutralization reaction because we're forming water. The only difference is that HF, the acid component, is a weak acid, so it has to stay together in the net ionic equation. All right, so there we go. Okay, what's next? Okay, so here's the special case for neutralization reactions, and that's forming a gas. There's still neutralization reactions because we are reacting an acid and a base. Is just sometimes that base isn't hydroxide. So instead of forming water, we form a gas. So in all of these examples, we're taking an acid like H plus, and we're reacting it with some type of anion. When H plus reacts with carbonate, you form H2CO3, which is carbonic acid. The name isn't important. What I want you to know is that carbonic acid is really unstable. It will immediately decompose into water and CO2. So the driving force in this reaction is actually the formation of CO2. That gas is pushing that reaction to make that gas forward. So carbonates will do this, all right, form a gas. You've done this, right? The baking soda vinegar experiment. Okay, vinegar is your source of H plus. Vinegar is bicarbonate, but it's basically a carbonate. So you're forming that unstable H2CO3, but it's immediately decomposing to CO2. So if you've ever done the vinegar and baking soda experiment, what observations do you make? It bubbles. Yes, it bubbles. Those bubbles are what? CO2 gas. Yes, very good. All right. So you'll see the same phenomena happen with sulfites. So essentially just change that carbon atom with a sulfur atom. So you make this a sulfurous acid. And so this is, again, is very, very unstable. It's analogous to carbonate. You get water, it decomposes, you get water and SO2 gas, right? And that SO2 gas is the driving force. The last one here is just a little bit different, and I guess it's a little bit easier, and that's reacting acid with a sulfide, right? So when you react acid with a sulfide, if you try to charge balance this, you'll get H2S. H2S is inherently a gas. So when you do the ion swapping, H2S is a gas. So again, that product is just a gas. So instead of using the solubility table, you won't find it. It's actually a gas on its own. So in all of these examples, forming that gas is that driving force. All right, so that's balancing. Our reactions turning sentences, names into chemical formulas. It's quite hard, and it'll come with practice, hopefully. Okay, all right, so got a little bit of time. Let's talk about conversions. So you got, half of you got a little bit of practice in lab on conversions, all right? So this is how chemists now, we can quantify how much matter we are working with. And this is important because when we do chemical reactions, we know that masses have to be conserved. Matter has to be conserved. So how do we know how much matter we're using? It has to do, we need a way to be able to weigh these things on a scale that's useful for us. We've already talked about atom masses, right? Like if we look at the periodic table, 12.01, we talked about, calculating atomic masses from isotopic masses and percent abundances. We talked about that in terms of AMU, that carbon, one carbon atom, its atomic mass is 12.01 AMU. The problem is in lab, I don't have an AMU meter. I don't have an instrument that can measure AMU. All the things that we have in lab that measure mass, measure in what unit? Grams, all right? And so chemists need a way to basically scale up everything to a point that we can actually measure. And AMU is way too small. We never work with single atoms, single molecules. So we actually work with a collection of atoms and molecules instead. We talk about working with substances in terms of Avogadro's number, 6.022 times 10 to the 23 particles. When I have a mole's worth of sample, I have 6.022 times 10 to the 23 particles. This idea is no different than me saying, oh, if I have 1 dozen of something, how many like individual units does that mean? 12, yeah, that's what we know. So it's the same thing. Chemists, we talk about this in terms of, dozens, because it's a lot easier to work with, you know, reasonable numbers versus, you know, tons and tons of particles. So this is Avogadro's number. We call this 1 mole, right? Or mole. All right, a mole's worth of substance is 6.022 times 10 to the 23. A dozen of something means 12. It's no different than that. So in the American Chemical Society, our mascot is a mole because we're not creative. All right, so it's like a little mole. You can take your picture with them, and then mole people. That's from what movie? The Incredibles. Yes, yes. The end of The Incredibles, but the beginning of The Incredibles 2, which was very good. And then Mole Man. Okay. Yes, and so the idea here is, okay, in chemical reactions, we never count molecules, okay? But the beauty here is I can say, oh, 2 molecules react with 1 molecule of O2 to give me 2 molecules of water. I can also talk about the same reaction in terms of moles. 2 moles of H2 react with 1 mole of oxygen, give me 2 moles of water. All right, so the reason for the significance of this number is it allows us to go up, scale up to the gram scale without changing the periodic table. I know that carbon is 12.01 AMU. But the periodic table also tells us the mass of a mole's worth of carbon. A mole's worth of carbon will weigh 12.01 grams. So we don't have to use a new periodic table as long as we're working in mole amounts. So that's the beauty here. We'll talk about molar mass here soon. So a single molecule, if you calculate how much that molecule weighs, so water, for example, is 18 AMU. It's a fraction of a gram. 1 molecule weighs 18 AMU. But if we scale up to a mole amount, that mole's worth of water is 18 grams, right? So we don't have a new table to worry about. So that's the great thing about this table. We can talk about it in terms of AMU per particle or a gram per mole's worth of that substance. Mole is abbreviated MOL. Okay. All right, so let's do some calculations here. So Avogadro's number and the idea of molar mass. So this idea, grams per mole, that is molar mass of our compound or of our element. A molar mass of something is simply the gram amount over the mole amount. So that's basically it. And that's the equation we're actually going to use for this next question. All right. So if we have, a fraction of a mole sample of cholesterol and it has a mass of this, what is the molar mass in grams per mole? So hopefully you can see it's just putting in the units in the correct place to give us the unit of molar mass. When you go to sleep tonight, say to yourself, molar mass has the unit grams per mole, grams per mole, grams per mole. And it'll be very useful to you. So we're just going to plug in these numbers. That 0.406 number goes where? On the top or the bottom? On the top, yes. Grams. And then that mole amount goes on the bottom, 0.00105 grams. I don't even have my notes. But I think it's like 300 something. Oh, is it on the bottom? No, it's not. Is it 300 something? Yeah. So when you do that grams, okay, that's why you're whispering. Moles. Sorry, there you go. Yes. So when you do the division, you get something like 387 grams per mole, meaning that 1 mole worth of cholesterol. See, we have a derived unit here. We can use this in dimensional analysis. What this unit means is that 1 mole of cholesterol will weigh how much? 387 grams. So whether we start in grams of cholesterol or moles of cholesterol, I can use this in dimensional analysis, put that 387 in the correct place to cancel my unit to get wherever I want to go. So there should never be, if you have drunk my Kool-Aid about dimensional analysis, you'll never have to ask yourself, do I have to divide by molar mass or multiply? When students say things like that, I know they're not thinking about the units. Because it should never be a question, do I have to multiply or divide, as long as you're always trying to cancel those units. All right, so that's the molar mass in grams per mole. What is the molecular weight in AMU of cholesterol? Did we catch it? What's the significance of the periodic table? It tells us 2 things, grams per mole, but also AMU. So if you were clever, what is the AMU mass of cholesterol? Just 1 cholesterol molecule. weighs how much? 387, what unit? AMU, yes, but I want to prove it to you. I'm going to prove it to you. I'm going to rewrite this value, the molar mass we just calculated. 387 grams of cholesterol is 1 mole. So I'm going to do some dimensional analysis. I have the conversions here for you. I want to convert grams to AMU. So I have that conversion right here. So the 1.66 number, is that going to go on the top or the bottom? The bottom, 1.6605 times 10 to the negative 24 grams is 1 AMU. So now I'm in the unit of AMU per mole, but I want this in AMU per molecule. So I'm going to go one step further and convert mole to molecule. So I'm going to use Avogadro's number. 6.022 times 10 to the 23 particles, is 1 mole. So that 6.022 number, is that going to go on the top or the bottom? The bottom, yeah, because I want to put that 1 mole up top. 6.022 times 10 to the 23. In this case, it's molecules. All right. So for fun, okay, before you come back here on Thursday, I want you to do that calculation and tell me what you get on your calculator. Hopefully it'll surprise you. All right. So have a good one. I'll see you on Thursday. Right? Class is over. Okay. Good. Oh.